Watch the physical motion of this rope. As the wrist snaps, a distinct wave pulse travels forward through the space. Look at the actual movement of the rope itself. While the wave's energy travels forward horizontally along the x-axis, the physical material of the rope is moving strictly up and down along the y-axis. This is a transverse wave, a type of wave where the medium moves perpendicular to the direction of the wave's travel. We can map that precise motion with a specific mathematical equation. Y as a function of x and t equals a times the sine of kx minus omega t. The a represents the amplitude, or the maximum displacement from the center, while the other variables define how the wave cycles through space and time. Notice that this entire wave exists perfectly flat against a two-dimensional grid. Because the string is confined entirely to the up and down xy plane, we classify this as a linearly polarized wave. But the y-axis is just one possibility. If you whip the string side to side instead of up and down, the vibration shifts into the horizontal xz plane. The mechanics are identical, but the wave is now polarized along a different axis. Now imagine a person twisting their wrist rapidly while whipping the rope, changing the angle of their throw in very short intervals. The wave's plane of vibration jumps chaotically in a fraction of a second. This multi-directional state is what we call an unpolarized wave. Because these vibrations occur in specific perpendicular directions as they move forward, we can theoretically filter them, which is a defining trait of all transverse waves. We can apply this mechanical model of the rope directly to light. Light is a transverse electromagnetic wave, where oscillating electric and magnetic fields take the place of the physical string. This head-on view shows natural light from the sun. It is unpolarized, meaning its electric vectors vibrate in every possible transverse direction simultaneously, creating a 360-degree starburst of energy. To filter that chaos, we use a material called a Polaroid. At a microscopic level, these sheets are made of long chain molecules aligned perfectly parallel to one another. These aligned molecules act as a directional barrier. They absorb any electric vectors that are oscillating parallel to their chains, leaving only the vectors oscillating perpendicular to the chains to pass through. This opening is known as the pass axis. When unpolarized light hits the first Polaroid, which we'll call P1, it strips away all the chaotic vectors except those aligned with the pass axis. What emerges is a single, clean plane of linearly polarized light. By forcing the light to vibrate in only one direction, this single sheet of plastic cuts the total intensity of the incoming light exactly in half. This leads to a specific question. What happens to this surviving light if we place a second, identical Polaroid further down the path? If that second Polaroid, P2, has its pass axis perfectly aligned with the first, the polarized light slips right through with no further loss of intensity. But as we rotate that second filter, the amplitude of the transmitted light wave begins to steadily diminish. We can explain this loss through geometry. The incoming electric field is a vector, and when it hits the angled pass axis of P2, only the specific component of the wave that aligns with the new opening can squeeze through. That component is equal to the original wave, E, times the cosine of the angle theta. This is the foundation of Malice's law. Because the intensity of light is proportional to the square of its amplitude, squaring that cosine function gives us this equation. Intensity equals the initial intensity times the cosine squared of theta. This graph shows how the energy drops as the angle increases. By simply changing the physical angle between these two sheets of plastic, we can precisely dictate exactly how much light energy survives. We can use this mathematical relationship to predict what will happen when the second Polaroid is turned to exactly 90 degrees. Since the cosine of 90 degrees is 0, the resulting intensity in Malice's law also drops to 0. Rotating two transparent sheets to be perpendicular creates crossed Polaroids. The overlapping square between them instantly turns pitch black, blocking the light entirely. This blackout happens because we have physically closed the only path for those sideways vibrations. If light were a simple forward-pushing pulse, like a compressed spring, rotating a slot would have no effect. The fact that a simple physical rotation can extinguish the energy confirms that light is shaking perpendicular to its path. Everyday commercial technology leverages this exact light filtering mechanism. When unpolarized sunlight reflects off a flat, horizontal surface like water or a highway, the light waves naturally align themselves. They bounce back as a horizontally polarized glare. Polaroid sunglasses use lenses with a vertical pass axis. They act as a crossed Polaroid against that horizontal glare, specifically targeting and blocking those reflections, while letting the rest of the vertical light pass through to your eyes. The same physics powers the entertainment industry, specifically the application of polarization in modern 3D movie technology. 3D glasses use two different polarization axes, one for the left eye and one for the right. This allows the screen to feed two completely separate image streams to the brain simultaneously, which we then perceive as a single three-dimensional image. From the mathematics of Malice's law to the screen of a cinema, polarization provides a precise tool for manipulating the hidden geometry of light.